We have learned who the physical attackers are, their motivations to attack, and the classification of physical attacks. Now we study the details of these attacks and some of the countermeasures. We start from invasive attack. Invasive attacks start with depackaging the chip or device to expose the inside of the silicon die. Decapsulation is the process of removing chip package. For complicated chips with multiple layers, deprocessing will remove layer by layer to allow attackers to study features in each layer. Once the chip is opened up, reverse engineering can be performed to discover the inner structure of the chip and its functionality. This can be done with an optical microscope with digital camera to capture high-resolution image of the chip surface in each layer. In order to obtain more detailed information about the chip, micro-probing station will be needed. This is perhaps the most expensive equipment required for invasive attacks. It can reach sub-micron precision, so electrical contacts with single on-chip bus line can be established without damaging them. This means that the attacker will be able to monitor on-chip bus activities, and they can also inject the tested signals and observe the chip's response. For example, secret keys or sensitive data can be extracted from memory by this method. Finally, with all this detailed information about the chip, a knowledgeable design team, and the silicon fabrication capability, the attackers will be able to rebuild or modify the chip to complete the invasive attack. For example, cutting certain internal interconnections can disable on-chip components such as encryption blocks. The cost to attack low-end chips such as old smart cards could be very low, but attacking modern chips requires expensive equipment and a very skillful attacking team. In addition, as the feature size keeps on shrinking for modern chips and its design complexity keeps on increasing, the cost of invasive attacks also increases very fast. We have mentioned some equipment for invasive attacks. Here is the list for your reference. Next, in the semi-invasive attack, the attackers also need to depackage the silicon to open up the chip. However, they do not need to create contacts with any internal signals. Therefore, the expensive micro-probing station and other equipment may not be required for semi-invasive attacks. Instead, the attackers will have to use other equipment to launch various semi-invasive attacks. For example, in the imaging attack, with the help from special cameras and photon probing, attackers can read the layout of the chip, localize the active regions, or read the logical state of certain CMOS transistors. In fault injection attacks, after locating the security fuses, the attacker can use UV light to reset these fuses to the unprotected states. In optical fault injection attack, the illumination of a transistor can make it conduct and thus introduce a transient fault or set the value of a single bit in the memory. This can be done with some very cheap laser pointers. Local heating can also permanently change some of the memory cells. With lasers, attackers can also write into SRAM or disable the write operation in the embedded flash memory. This is called memory masking. We will discuss side channel attacks in details next week. Optical equipment and the techniques can make side channel analysis much more accurate and deadly. For example, laser can be pointed to a particular transistor. This allows the attacker to collect the power trace before and after using laser and then compare. These are the set of tools and equipment that might be useful for non-invasive attacks. There are 4 types of non-invasive attacks. Side channel analysis. This is the only passive attack, as it only monitors the chip's execution and collects some measurement. Brute force attack is a strategy for search information on the chip. It is normally an organized search instead of a random search. For example, attackers can search for secret keys and password if they are not sufficiently long, or their memory address can be predicted or are restricted to certain areas. They can also try to rebuild the truth table of input-output pairs to reveal the functionality of the design. Of course, this will be limited to relatively small designs. By applying high voltage, normally it doesn't have to be very high, just about twice as the normal supply voltage, or inject random signals or commands, attackers may gain access to factory testing or programming mode. These access are known sometimes as backdoors. The other 2 types of non-invasive attacks are known as data reminiscence and fault injection. We will discuss them next. These last attacks all need interaction with the chip, and therefore they are all active attacks. When secret keys or data are stored in SRAM, they may leak in several ways because of the physical characteristics of SRAM. First, after power is down, SRAM will still retain the data for a short period of time, so the attacker can try to steal the data during this period. On the other hand, when data has been stored in the same location for a long time, it may appear after the chip is powered up again. This gives the attacker the chance to view the data. Finally, data in SRAM can be frozen in low temperature. Most commercial devices consider -20 degrees Celsius or below as tempering stage, but there are ways to make data freeze at higher temperature and then read it out. Data reminiscence can also happen in EEPROM or flash memory. The threshold voltage will change after each write and erase in such memory. It has been reported that data can be extracted after multiple write and erase cycles. The idea behind fault injection attacks is to manage the chip to run with faulty data or unexpected instructions, and then observe the execution to gain unauthorized access to systems or learn secret data. It is possible to input faulty signal directly from the input-output interface, but secure systems can easily detect such faulty input before the execution starts. So how can attackers inject faults? There are actually many ways to do that. We will talk about clock and voltage glitches in details on the next slides. By changing the temperature or exposing the chip to white light or laser, the states of the transistor or the flip-flops may change. This can also be done by using X-ray, ion beams, or EM flux. A glitch is a fast change in chips supplying signals, such as supplying voltage and clock clock signals. It may affect some random transistors or flip-flops. Although the attacker may not have control on which transistor or flip-flop will change, it is not very hard to do a systematic search to find security holes. For example, a shorter clock pulse causes incorrect instruction fetch in Motorola controllers. And power supply glitches can break a 128-bit AES key in 2 to the power 12 attempts, which is about 8 hours at a 100 millisecond cycle. If we do it selectively at carefully chosen time slots, not continuously, the number of attempts can be reduced further to 2 to the power 7, or only about a couple of minutes. Fault injection attacks are based on faults, so fault-tolerant computing techniques can be used to defend them, both at software level and hardware level. However, this does come with overhead in hardware and performance. Also, sometimes detecting fault injection attacks after the attack might be too late. The damage may have already been made. For example, attackers may have already learned information about sensitive data. It is preferred to detect the faulty condition before the system executes under such conditions. This is a very challenging problem. Now we talk about some of the countermeasures to invasive attacks. Some of them may also be applicable to semi-invasive attacks. First, recall that attackers can probe at a single bus line to steal data. Almost all the data buses that connect the CPU and the memory are either in the increasing order from 0th bit to the highest bit, or in the opposite order from the highest bit to bit 0. This makes it easy for the attackers to locate the bus line they want to probe. We can change this order to confuse the attacker, which is known as bus scrambling. We can also encrypt sensitive data to prevent the attacker from probing it. Of course, the data after encryption needs to be decrypted in a trusted zone before it can be used. Another way to defend invasive attack is the new glue logic design approach. In this design style, standard building blocks such as register files, instruction decoders, arithmetic and logical units, and input-output circuits are glued together like an ASIC instead of individual components. This hides the data bus, so it becomes impossible for attackers to find the signal to attack. To protect from invasive attacks, most of the smart cards have a sensor mesh implemented in the top metal layer. All the passes in the mesh are monitored continuously. Microprobing attempts will cause short circuits. This will trigger an alarm, and the memory contents will be reset to protect sensitive data.